I would start by thanking the organizers for this wonderful program. I enjoyed very much. It's a bit sad that this is the last week we're here. So my topic has been introduced from many different angles. Some parts were introduced during the previous weeks, some already here at the conference. And I would like to first acknowledge many people that contributed to parts of this work, and in particular Robert Babiak, which is my PhD student that's currently writing his thesis. So his thesis is on direct laser acceleration, and he has done a big chunk of the work presented here. So I'll do my presentation the other way around, because we were asked by the organizers to mention the code capabilities. And this will be a little bit more brief. So since you've already heard about peak codes, you've heard about scale separation. So we also have scale separation problems in laser plasma interactions. It's just our scales are all much smaller, but we very often have to cover from microns to centimeters. We have to use multiple dimensions. Many problems do need 3D full-scale treatment. We need a lot of particles to be able to have enough statistics for the microphysics. So this means you need a code that scales very well across multiple architectures. And clearly to be able to take advantage of the biggest supercomputers that you have available. And so I have not introduced details about particular scalings on different machines, but I think we've run on most big machines in Europe and the US. So in particular, I decided to focus on the part that's related to these extreme plasmas. So you have seen these plots, this slide before shown by Thomas in the previous week. So the standard peak loop is the same as in your astrocode. So we have the fields live on a grid. Particles are free to explore the full 60 phase space, and fields are advanced through Maxwell's equations, and the particles are pushed by the Lorentz force. So if you want to include extreme interactions, so first thing to do is to include, for example, a classical radiation reaction. This is when your particles are suffering a drag due to the radiation emission, and this can be done just by adding a drag term on the Lorentz force when pushing the particles. Then we can, if we're in a quantum regime, have nonlinear Compton, or I'm going to do this. It's easier, yeah. Okay. So we can have a nonlinear Compton and nonlinear Bright-Wheeler. So just to remind you, already heard about these processes. So we can have an electron, highly relativistic, in a very strong background, emit a photon. This photon is a hard photon. It cannot be propagated on the grid. So think of a gamma ray, and then this gamma ray in a strong background can decay into an electron-positron pair, making through this nonlinear Bright-Wheeler process. So even the previous speaker mentioned the particle merging algorithm. When you are simulating, for example, QED cascades with lasers, you get an exponential rise of the number of particles in the system. So we need to have a way to resample them. So we basically have a way to preserve the phase space and add just more weights to some particles and remove the excess particles. Then linear Compton scattering is when you populate your space with many of those hard photons, there is some probability of them colliding with each other and redistributing energy. So this is another process that is included. Then we can have Bremsstrahlung and Bethe-Heitler. So this is analog to this nonlinear Compton and Bright-Wheeler, but now in high Z targets. This has also been mentioned. We also have an Euler-Heisenberg solver that allows to look into quantum vacuum polarization. And finally, if you want to study some astrophysical setups, sometimes the scale separation is so large, especially in temporal scales. So you can also put heuristic pair emission and photon emission and pair production rates, so that you can have global simulations looking at the qualitative effects, but in that sense, your processes would be faster than in reality. So these are mostly algorithms that are applied on particles. So they have an event and then they participate in a global plasma dynamics, and they can be coupled with non-Cartesian geometries such as quasi-3D or spherical to do simulations. We also have a quick calculation toolkit for laser electron scattering. So you've seen Tom was talking about these type of experiments. So in experiments you have offset longitudinal and transfers because you cannot always hit a perfect sweet spot to overlap your beams, your laser and the electron beam. So your experimental results have different values, effective values of intensity that will actually happen in experiments. And you, to analyze hundreds of shots, you sometimes would need hundreds of 3D simulations, which is completely unpracticable. So based on some analytical calculations, we have also developed a fast calculation toolkit that can do this approximate calculations very quickly. So it's good for parameter scans. Okay, so I'm going to now dive into the physics. So I'm going to tell you about direct laser acceleration of electrons, then how we can create positrons and accelerate them with direct laser acceleration as well. And then I'm going to discuss what are the radiation signatures of this acceleration process. You will see there are some similarities here with what you see in astrophysics. So I'm going to first introduce the physics of direct laser acceleration, but starting first, why do we want to accelerate electrons in the first place? Electrons are incredibly useful. They have applications in medicine, for example, in cancer treatment. They have multiple applications in industry. They're very good for imaging. They're also in environmental treatment of flue gases. They're used to neutralize the harmful elements. Then, in particular, for us, what is interesting is the scientific part. So, electron beams are useful as radiation sources. They're useful as a secondary particle for secondary particle generation. They are used in material and science and safety of nuclear devices. And this is just to mention a few. But what we are interested in, obviously, is applications in extreme plasma physics. So this is why we do it. So why with direct laser acceleration? So what is good about this particular setup is that we get really lots of electrons in these beams. So what you usually think about when you think plasma acceleration of electrons, usually people think of Wakefield. This is the standard way to do it. They can provide quasi-monoenergetic beams, but direct laser acceleration can provide 3 orders of magnitude more charge in the beam. But there is no free lunch, so the price we have to pay is that the electron beam spectrum is wide. Okay, so we don't get a monoenergetic beam at a few GeV, but we get a very wide spectrum, and this is these are 2 experiments that have shown 100 nanocoulomb and almost a microcoulomb with DLA. So we know we can use these beams for applications that don't require monoenergetic spectrum. So the physics works like this. So we're an ion channel. So imagine that you have electric field that's radial. So we have a channel axis here. The electric field is pointing towards, not towards the axis, away from the axis, but it pushes electrons towards the axis. And if the particle starts moving at a certain angle in this channel, it will naturally perform oscillations in this electrostatic potential. So I'm saying electric field, but this can be magnetic field as well. It doesn't change anything. It's just the point is that there is something that pushes particles towards the axis. And now we have a laser field. So a laser is co-propagating with a particle. You can think of it as a plane wave co-propagating with a particle. And then, so these oscillations will have another set of oscillations coupled, so on top at the same time. And so we don't have longitudinal field, which means that here this would be just oscillations, there would be no acceleration. But if we have a situation where particle is anti-parallel in transverse momentum with the electric field, we can have energy gain. So what happens is that there are these small sections where particle can stochastically gain energy or lose energy. So this is the field structure, how field structure looks like. So there is a radial electric field and an azimuthal magnetic field. If you evacuate electrons either sideways or create a current that goes forward, and both of these fields act to push the particles toward the axis. So if you do the math of this motion, it turns out you can write a Hamiltonian for this system, and you can extract a conserved quantity, which looks like directly composed of two recognizable textbook examples. One is a harmonic oscillator. If you have just electrostatic potential, you would expect simple oscillations, where this is where the total energy is conserved. And in here you have, for a plane wave interaction or wave packet interaction with the particle in vacuum, you have canonical momentum conservation from which you can derive that this energy minus normalized parallel momentum of the particle in the direction of the propagation of the wave will be conserved. So in the case of coupled oscillations, we have this other quantity that's literally a combination of the two that is conserved. This is, of course, the case if you don't have radiation losses. Okay, so this is a simple case where everything is well behaved, and you can calculate what is the frequency of the betatron oscillations. So it's reversely proportional to the energy of the particle, of a square root of energy of the particle, and it turns out that how the laser frequency is observed by the particle depends linearly of this integral of motion, and is reversely proportional to the energy of the particle. So this gamma, the Lorentz factor of the particle energy, is local Lorentz factor. So as the particle accelerates, these frequencies change. And if you want to have let's say perfect acceleration, so the best thing to do is to have these two frequencies the same, and then you can extract what would be the gamma you would get with this perfect resonant acceleration. So it turns out that if you have this process where you can have accelerating, then a decelerating half cycle, then accelerating and decelerating half cycle, actually the only place where you can retain energy is when the momentum changes polarity at the same time with the electric field. So it means that if you look at the transverse phase space, you expect particles. So it's not transverse, it's the trajectory of the particle in the transverse phase space. You have the energy gain happens at the furthest point from the axis, where the particle is reversing the direction of motion. And this is where you can obviously see how the frequency ratio changes. And you can have a less efficient or more efficient acceleration. And even though, if you look at this, the resonant energy that you expect to achieve, here it doesn't explicitly depend on the laser intensity. Just to remind you, this is this integral of motion. What will depend on the laser intensity is how much energy you can transfer in this one reflection. So the intensity will ultimately affect the energies we expect. So I'm going to show you a movie here of the particle trajectories. So here is the laser envelope. It's parameterized by A naught, this normalized vector potential that was defined in many talks before. This is just a longitudinal versus transverse coordinate. Here is to look at the energy. So this is the limit that we expect, maximum allowed. And this is the longitudinal distance. And here we're tracking this conserved quantity in two sections just to see if it's really conserved, which we can verify. So you can see that in the beginning, particles are off resonance, so they don't almost gain any energy. Then slowly getting closer to the resonance and then resonance motion, they go up to this maximum energy. And then, so what happens is the gamma factor goes, overshoots this typical energy that we expect. And then the frequencies again detune, and then there's decelerating stage, and then it goes back to accelerating stage and so on. So if you don't have any radiation losses or no structure in the plasma, so if you're in a flat density plasma, you will have this kind of picture. So how do you optimize this? Well, so what matters is that your maximum energy that you can achieve actually depends on the distance of from the axis where the particles reflect. So the higher the radius of the oscillations, the higher the energy. And your intensity of the laser actually controls how far from the axis particles can oscillate. So if you are just thinking about intensity, so people like to, in the lab, obtain high intensity by focusing very tight. But then you will have a very low spot size, and then maybe this radius will not even fit in the spot size of the laser. So sometimes, just by increasing the spot size, if you would be, so in simulations you can do that, is increase the spot size and keep the intensity the same. You cannot obviously do it in a real laser system, but you can see the increase on the particle energies just by doing that. So it's not just the intensity, it's not, the picture is not that simple. So what you should aim for is to have this spot size. So if you have a specific laser system, you should have a spot size matched to this natural oscillation radius that you can support with a certain intensity. And so if you focus too narrow, you will be missing out because you're limited by the distance that particles can oscillate on. If you focus too wide, you will still, this natural distance will be too much in the laser, and you will not be using this energy on the edges. So best thing is really to match this natural distance with the spot size of the laser. And then you can make a map for the current and near future laser facilities, which are, let's say, 1 petawatt is available in several labs in the world now. 5 petawatt is kind of getting really close. And 10 petawatt, well, 10 petawatt, it has been commissioned in Romania, but I think that the experiments are not yet using 10 petawatt, but we're not that far. Okay, so usually people are, when they think about these systems, they want to focus to the diffraction limit, which is, so if the wavelength is a micron, let's say it's 2.5, 3 microns spot size. But it turns out that for this application, it's better to have a wider focus, above 5 microns and more on the order of 10 microns. And for higher power lasers, much bigger than that. If you have this optimal, so you can work out directly, analytically, what would be this optimal spot size to use for any combination of the plasma density and the laser system, so having the power in mind. And you can see that A naughts we are operating at are somewhere on the orders of between 20 and 50. It can be hundreds for the 10 petawatt systems if we go to higher densities. And the energies we can expect for the particles is on multiple GeVs, potentially if we manage to use low density targets, we can have very high energies and even excess of 20 GeVs. The problem is that there is if we want to go for here, we will have to guide the lasers for 100 millimeters, which is not in a low density plasma, which is not an easy feat. So actually, probably we will go for this region of the parameters where we have a density of about 10 to the 19 particles per cc. So 1% of critical density, and go for about between 5 and 10 GeVs. And this can be done with a millimeter target. So we're limited. If we go to much higher densities, we will be limited by radiation reaction. And this is because we have, so the particles are propagating in the background channel field, and they are oscillating, and they keep emitting. So the radiation reaction limits ultimately the maximum energy we can get to, but sometimes this limit is not very low. So, and there is one added benefit of radiation reaction. It changes the oscillation properties of the particles, so actually it can help get into the resonance. Just to give you an idea how important it is to know all these multi-factor optimization parameters, is that you see here we have, so this is what we have shown with our simulations. So we have shown that near future facilities can get to 10 GeV. But you can see, so these are, this plot has experiments and simulations in this field. This is the predicted energy. This is, these are parameters that are important for this maximum energy that one can get. You can see that in experiments, 1 petawatt laser experiment sometimes gained lower energy than 10 terawatt laser experiments. And this is because they did not have access to this optimization strategy, because they either had a too small radius for the laser pulse, or they didn't have a long enough acceleration distance, because you have to allow time for particles to get accelerated, to get into this resonance. So and even in simulations, so the triangles are simulations from other publications, it's not evident to get to this optimal energy. Okay, so this line, the dashed line, is 1 order of magnitude lower. So that's why it's very important to have these studies of microphysics. So you can extend the theory to varying density profiles, and in that case, you're changing this integral of motion that also gets changed when you have radiation reactions, so you can tune the oscillations better this way. We can predict what's the energy gain possible with the density varying profile, even if the laser has a very complicated intensity modulations over the propagation. You can predict these energies with a reasonable accuracy. And what you can use this for is, for example, to shorten the required acceleration distance by combining 2 different densities, or to avoid the radiation reaction limit once you have accelerated particles enough. So you can put it to a lower density after. So I promised to say what this is useful for. So we can create positrons and accelerate them with DLA as well. So you have seen that pairs can be created with this Bright-Wheeler process. So we can do this in scattering experiments at 180 degrees, but we can also do it at 90 degrees. And then this is a bit less efficient, but it still creates pairs. And then those pairs can be accelerated in the direction of the laser propagation and separated from the initial electron beam. However, here, if you do it, so you can do this in vacuum, but in vacuum you're limited by the acceleration only in the Rayleigh range. So what you could try is to do the same thing. You scatter the laser and electron beam at 90 degrees, but then send the products into a plasma channel to undergo DLA. And it turns out that radiation reaction is very important in this step, because if you want to deflect the particles towards the channel, you really need them to lose energy, because if you're creating them at 90 degrees, you need to have a certain initial energy on the beam to have a reasonable conversion efficiency. And then this means that pairs are created with high transverse momentum, and they need to lose it to be able to be deflected towards the channel, which is good. So this is, the design is for L4 Eli laser of Czech Republic, which will have 1 kilojoule and in 150 femtoseconds, we'll be able to use high ANOTs to do that. So what happens is once you manage to create and send the electron positron beam into the channel, it propagates on top of the laser. But the laser is still going to pick up particles on the way, so the electrons of the plasma, and will have a significant beam loading, which you can see here. This is the charge density below, and up is the magnetic field. You can see that there is a polarity of the field is reversed. Actually, what we're seeing here is not just magnetic field, we're seeing the direction of the Lorentz force. So the red is what's normally in the channel, which is focusing for electrons, defocusing for positrons, but due to the beam loading, we have a section that is focusing for positrons and defocusing for electrons. And then we are able to put positrons through standard DLA in the channel. So I'm just going to show this in a video. So you can indeed do that. And you can also explore different configurations to create those positrons. So you can shoot a high Z target instead of doing the 90 degrees collision and then put everything in the channel. You can also put a target in the channel once this focusing structure has already been formed. So then you can improve the retention of your particles this way. Or you can just fully accelerate electrons and then shoot the target in the end, just similarly like the Wakefield beams are shot to create particles, to create pairs. So the difference is that now we will have much more particles doing this interaction. So what we have done, we looked into this two-step process. So we used OSIRIS to accelerate electrons with DLA. Then we used Gen4 to calculate the propagation through the thick target, because this was a very long thick. We can do this in OSIRIS, but for thinner targets. And then we have put it back in OSIRIS to see if it filaments. And indeed, we have shown that the realistic beam with the proper with the divergence and the realistic shape is indeed able to filament in the background plasma. So we get a beam with similar properties in terms of, so it's not fully neutral, but it's quasi-neutral. And this shows a promise for laboratory astrophysics applications. And in the end, I'm just going to finish with radiation, how the radiation looks like. So if you're in optimal conditions for DLA, you can work out that your radiation critical frequency is going to be proportional to A0 to the third, and that at low densities you will have very common-limited radiation, while in high densities this radiation will be a bit more wider. And this scaling works across many different parameters, so different densities, different intensities. And I'm going to finish here and take your questions. Thank you very much for your attention.
So we have plenty of time for discussion. Questions? Maybe I'll start on the radiation. So what kind of spectra are you expecting to get out of these setups?
So we are getting typical synchrotron-like spectrum. This is incoherent radiation, and during the acceleration, so this is a long process where we have a wide beam. So we can, but most the radiation at high energies is mostly governed by the highest intensity, highest energy particles. So we can predict, if you look at the end of the spectrum, so the cutoff is well predicted by this critical frequency that we can calculate using our expected gamma.
Yes.
Thank you. So it seems to me you focused more on classically underdense regime when electron density is below the critical density. In the more recent papers by Alexei in particular, I think they're suggesting maybe efficient acceleration process when you go classically slightly overdense or comparable densities. Could you comment, like, which one is better strategy? Because I understand magnetic field is stronger when you increase the density. Of course, you increase the losses, but is it really bad?
So it's slightly different regimes. The answer, which one is better, it depends what you want to do. So if you want to go to the highest possible energies, which was our goal here, it's better to go in low densities because your radiation limit is higher. Okay, so we wanted, so our goal is to take as many particles above 1 GeV as we can, because then this allows us to have higher number of electrons, positrons, and also other type of particles when we interact with solid targets. But the regime that Alex is exploring is, let's say, more efficient. If you want to convert a lot of energy to radiation, it's better to go to higher densities, because then you just have lots of radiation and therefore also lots of radiation reaction.
Okay. And the magnetic field, sorry, just one more clarification. The magnetic field that you generate by the current is going to be strong. Like when you talk about betatron oscillations, it's mostly electric field that is doing it?
No, it's both. So you have, if you're in low density regime, your electric and magnetic field are roughly the same order. If you go to high densities, it's mostly magnetic field.
Yeah.
The electric field can be orders of magnitude lower. But they do exactly the same thing. So you can, if you have E and B, they're just adding together the force towards the axis, because they're oriented in a way that push electrons towards the axis, both of them.
Okay, thank you.
Questions, comments? Yeah, please.
I guess because this is the numerical approaches section, I see your simulations here are in 3 dimensions. So I don't know if they, maybe you could tell us about the quasi 3D, because I presume you might have used that. And I guess it's kind of a unique geometry for the laser plasma community, but I think it's still interesting nonetheless.
Yes, okay. So these simulations would be completely impossible to do in full 3D, because we're talking millimeters of propagation, where you have to resolve microns in each direction because of the densities we're looking at. So we are using quasi 3D, which is you have a Fourier decomposition of the modes for the field, but you're actually in terms of space, you're simulating just you're simulating a 2D grid, and you are assuming it's not really a cylindrically symmetric geometry, because there are all those extra modes that can capture like linear polarization or some structure. So if you include infinite number of modes, you could reconstruct full 3D, but we're just including the number of modes we need for a particular problem. And this allows to push this DLA simulations to a different scale. Yeah.
So just to clarify this. Sorry, thank you. Thank you. Just to clarify this, so do you mean that you have a grid in, so you have cylindrical coordinates, let's say, and you have a grid in R and Z, but some number of, finite number of modes in the azimuthal angle, right?
Yes,
okay.
Yes.
Thank you.
Yes, any more questions, comments?
How many modes? Well, so if you're in underdense plasmas and you don't have filamentation and so on for the happening, you can get away with 2-3 modes. If you are simulating some very complicated interaction where there is a lot of oblique motion and interaction with high density targets, you will need more. Yeah.
I think we'll hear more about the quasi 3D in the next session, and one specifically on jets, as far as I think. So I think this will be a very nice connection here. Any more comments, questions? Well, if not, I think it's coffee time. So let's thank Marija. Thank you very much. Thank you.